Hello, and welcome to the first lecture on an introduction to graph theory or network theory. Graph theory is a really interesting subject with lots of applications to things like computer science, chemistry, social networks, and genomics. Basically, anytime you have relations or connections between a set of objects or a group of people. I hope you'll follow along these lectures using the handouts that should be provided on the page where you found this or linked down below. And as we're going through, I'll ask you to pause the video a lot so that you can think about the problems we're doing before we talk about them together. So we'll start this by talking about the problem of the Bridges of Konigsberg. So the city of Konigsberg, that's in this map here, consisted of two sides of the Pragal River and two large islands. And they were all connected to each other by 7 bridges, which are highlighted in orange here. Now it's said that the people of Konigsberg would walk back and forth across these bridges, and they would wonder, is it possible to walk across each of the bridges once and only once? Now you can try to trace paths like this on the map that you see here, and see if you can draw a path where you walk across each of the bridges once and only once. So either it's possible and you're able to come up with a path like this, or it's not possible. However, just because you can't find a path doesn't mean it's not possible. You would have to come up with some sort of proof for why it's not. So the mathematician Euler, who was staying in Konigsberg, decided that he would try to solve this problem. What he noticed is that the size and the shape of these land masses didn't make a difference in whether or not this was possible. He also noticed that the length of the bridges didn't make a difference. All that mattered here was connectivity. So you can imagine that each landmass is just reduced to a point. And the important information is how these points are connected to each other. So I think of the bridges as connections, and we can draw those connections as a set of lines. One line for each bridge. And in this way, we've represented all of the important information in trying to solve this problem as a set of points and lines. We can redraw this down here. We have our 4 vertices representing the 4 land masses, and we have our 7 lines representing the 7 bridges. And by doing this, Euler invented what's called graph theory. So what we've just drawn is called a graph. It's a finite set of vertices, which are the points or the objects, and edges, which are the lines or the connections. So the number of edges connected to a vertex V is what we call the degree of the vertex, and we denote it by DEG of V. So let's look at this graph here in the example. What's the degree of V in this graph? Well, V is connected to 3 edges, so the degree of V is 3. What about the degree of W? W is connected to 4 edges, so the degree of W is 4. So we can ask this question, for which values of n can we draw a graph on n vertices where each vertex has degree 3? So I want you to pause the video and try to figure out these 2 questions. First, can you draw a graph on 4 vertices where each vertex has degree 3? And second, can you draw a graph on 5 vertices where each vertex has degree 3? Now, it's not necessarily possible to answer both of these questions, or there's not necessarily a solution to either of these questions. So see if you can draw one or see if you've given up and then come back after pausing the video. Okay, so now that you're back, let's see if we can figure out these questions. So first, can we draw a graph on 4 vertices where each vertex has degree 3? Well, we can draw in our 4 vertices. and then connect them with edges to try to get each one to have degree 3. So we can start by drawing in some edges. Now each vertex has degree 2, so I need to add in more edges. And we get this graph where each vertex has degree 3. Each vertex is connected to 3 edges. And yours might look a little different from this one, that's okay. But now we go to a graph on 5 vertices. And we want to know if we can draw one where each vertex has degree 3. So we can start by drawing in some edges. Okay, each vertex has degree 2 now. We can add in some more. And now we've reached a problem. So 4 of the vertices here now have degree 3, and this vertex here still has degree 2. If we draw in another edge, that's going to make the degree of these other vertices, whichever one we connect the edge to, equal to 4. So we can't do it, at least with what we've already drawn here. And you can try some other ways, starting with different connections between the vertices, but you probably weren't able to do it. So we'll say no, but just because we can't find an example doesn't mean it's not possible. We would need some kind of theorem to prove that we can't do it. So we'll see if we can use what's called the degree sum theorem, or the handshaking theorem. We'll let G be a graph with n vertices, call them v1, v2 through vn, and m edges. Then if we take the sum from I equals 1 to n of the degree of vi, so what this is the sum degree of v1 plus the degree of v2 all the way through the degree of vn, the sum of the degrees of all of the vertices, we get 2 times the number of edges, or 2m. So why does this make sense? Well, we'll think about what each edge does, what it contributes to the total degree of each vertex. Well, each edge is connected to 2 vertices. It has 2 endpoints. So each edge contributes 2 to the sum of the degrees of the vertices. Therefore, in total, we get 2m is the sum of the degrees of all of the vertices. So each edge contributes 2 to the sum of the degrees of the vertices. So now, can a graph have an odd number of vertices of odd degree? Well, let's think about this sum on the left here. We're adding up the degrees of vertices. What if each of these degrees is odd? If we add an odd number to nothing, that's going to be odd. If we have odd and odd, what do we get? We get even. And if we have odd plus odd plus odd, that's odd again. And this is going to alternate. So if we add odd numbers an odd number of times, we're going to get an odd number. But why is that a problem? Let's look at what this has to be equal to. The sum of the degrees of the vertices is equal to 2m. 2m is an even number. So adding an odd number of times gives us an odd number, but it would need to be even by the degree sum theorem. So this is not possible. So a graph cannot have an odd number of vertices of odd degree. So to answer our question from earlier, can you draw a graph on 5 vertices where each vertex has degree 3? The answer is no by what we just said, and also if we plug into the degree sum theorem, what's the sum of all the degrees of the vertices? It's 5 times 3, but that has to be equal to 2m. It has to be an even number. So 5 times 3 is 15. It's not even, so this is not possible by the degree sum theorem. So that's a way of proving that the answer to this question is no. Okay, So now we say a vertex V is adjacent to a vertex W if they're connected by an edge. So in this example, is V adjacent to W? Well, V and W are connected by an edge, so the answer is yes. And that's a single edge. But is V adjacent to X? Well, we can get from V to X by following multiple edges, but there's no single edge that connects V and X, so they're not adjacent. So now a set of distinct edges, E1, E2 through EK, distinct means that none of these are equal to the others, is called a walk if we can trace these edges in the graph without picking up our pencil. So in other words, the end point of edge EI is the starting point of the next edge EI plus 1. So let's look at this example. Why don't you pause the video for a second and draw a walk in this graph from V to W. So now that we're back, we'll draw a walk from V to W. What we want to do is follow along or walk along the edges without picking up our pencil, starting at V and ending at W. And there's obviously more than one answer for this graph. You could also go this way, for example. Now this walk is closed if it starts and ends at the same vertex. And if a walk uses all edges of a graph, we say it's an Eulerian walk. So let's look at this graph here. Is there a closed Eulerian walk in this graph? Why don't you pause and try to draw one? Okay, now that you're back, we want a closed Eulerian walk. So closed means we start and end at the same vertex. Eulerian means we use all the edges of a graph. And a walk just means we don't pick up our pencil and we don't go through the same edge more than once. So you can start anywhere you want. I'm going to start at this vertex and I'm going to walk along the edges and try to get back to where I started without going over any edge more than once. And we want to use all of the edges. So let's go up here and we have to go down here. Now notice we don't want to go back across this edge because then we won't have used all of our edges. So we need to go up, continue this way, and then back along the bottom. Okay, so we've covered all of our edges. We ended up where we started, and we didn't use any edge more than once. That's a closed Eulerian walk. If a walk doesn't go through any vertex twice, it's called a path. So notice this walk that we drew here, this is not a path because we go through this vertex twice. We went through when we entered up here, and then we went through again when we were going through the edges on the bottom. So look at this example. Is there a closed path in this graph? If so, draw one. So why don't you pause and try to do that? Okay, now that you're back, let's see if we can draw a closed path in this graph. So we want to start and end at the same vertex. Okay, and we don't want to use any edge more than once. And we don't want to go through any vertex more than once. So you go up here, go over here, back down, and then back across. So yes, this is a closed path. We didn't go through any vertex twice and we didn't use any edge more than once. Now try to see if you can find a closed Eulerian path, meaning we go through all of the edges. Why don't you pause and do that now? I am going to erase these. Okay, and then draw again. All right, let's see if we can find an Eulerian path, meaning we want to use up all of the edges. So let's try to start here. Let's go along this edge. Then let's go along this one. We have to go back down here. And now we want to end up where we started, so we want to go to this vertex, but we also want to use all of the edges. And here that's not possible. If we go along this edge, we'll end up back at this vertex we already went through. If we go along this edge, we won't have used this edge. Whoops. So what's the problem here? What can we do to this graph so that there is a closed Eulerian path? Well, let's look at this vertex. And let's think about what has to happen in a closed Eulerian path. If we go visit a vertex, anytime we enter it, we also have to leave it. And we don't want to enter it again, because then we'll be visiting that vertex twice. Therefore, the fact that this vertex has degree 3 is what gives us a problem here. There will only be a closed Eulerian path if the degree of each vertex is 2 or less. And in fact, the degree of each vertex will have to be 2. Okay, so suppose we want to see if there is a way to walk across each of the bridges from our original problem once and only once and end up back where we started. Let's interpret this problem. We'll call it problem 1 in terms of our new definitions. So why don't you pause and try to write that down. So now that you're back, we want to walk across each of the bridges. Okay, so that means we want it to be an Eulerian walk, once and only once, and end up where we started. That means we want it to be closed. So our problem is there a closed Eulerian walk in our graph? And we'll see how we can figure this out. So we say a graph G is connected if for any 2 vertices x and y of G, we can find a path from x to y along edges of G. So I want you to try to draw 2 graphs, one that's connected and one that's not. Why don't you pause and then come back? Okay, so now that you're back, let's first draw a connected graph. Let's say we have 3 vertices. Okay, and we want to have a way to get from x to y from any 2 vertices, from any vertex to any of the others along the edges of our graph. So if we add an edge here and we add an edge here, all of a sudden this is connected. Now let's draw one that's not connected, still have 3 vertices. Okay, let's say we put an edge here. If I put in any other edge, then all of a sudden there's a way to get from this vertex to the other 2. But notice as it is now, there's no way to get from this vertex by going along edges to either of these 2. So this graph is not connected. And you can see why this one is called connected and this is called not connected. So let's use this theorem to try to answer a question from before. Let G be a connected graph, then G has a closed Eulerian walk if and only if all the vertices of G have even degree. So this is what we call an if and only if statement. We can interpret it as 2 separate statements. The first one is if all vertices of a connected graph G have even degree, so that's this part of the statement right here that we're assuming, then G has a closed Eulerian walk. So then this part of the statement is true. And we also get the following statement. If a connected graph G has a closed Eulerian walk, so we assume this part of the statement, if that's true, then all vertices of G have even degree. So then we get this second statement here. So if one side of this if and only if statement holds, the other must hold. In other words, if one side is true, the other side is true. But similarly, if one side of the statement is not true, the other side is also not true. So let's say not all vertices of G have even degree, meaning at least one has odd degree, then G does not have a closed Eulerian walk. So what does this theorem tell us about the answer to problem 1? Problem 1 was, is there a closed Eulerian walk in our graph? Let's redraw our graph so we can look at it here. We have our 4 vertices, our 4 land masses, and then the 7 edges representing the bridges connecting them. So our theorem tells us that G has a closed Eulerian walk if and only if all vertices of G have even degree. So do all vertices of G have even degree? No. This vertex, for example, has degree 3. So not all vertices of G have even degree. So G does not have a closed Eulerian walk. And I forgot to mention also, it's important that G is a connected graph. If it weren't, then we would not have this statement. Okay, so now suppose we remove the requirement to start and end at the same place. Let's interpret this problem in terms of our definitions. So why don't you pause and try to answer that on your own. Okay, so now that you're back, all that we're removing is the requirement to start and end at the same place. So we're not requiring that the Eulerian walk is closed anymore. So our question is, does G have an Eulerian walk? Okay, so we can use this theorem to help us determine if our problem has a solution, or we can answer this question that we wrote down. So if we let G be a connected graph, then G has an Eulerian walk starting at vertex X, that's just any vertex, and ending at vertex Y, some other vertex, if and only if the degree of X and the degree of Y are odd, and all other vertices of G have even degree. So what does this tell us about the answer to problem 2? Well, X and Y can be any 2 vertices. So what we're looking for in our graph is 2 vertices that have odd degree, and all of the other vertices have even degree. Okay, so let's look at the degree of each vertex. This vertex here has degree 3. This vertex has degree 3. This one has degree 3, and this one has degree 5. So we don't have 2 vertices of odd degree and the others are even. Therefore, G does not have an Eulerian walk. So all of the vertices, all 4 vertices of G have odd degree. So G does not have an Eulerian walk by theorem 2. Okay, so that's the end of this lecture. I hope you enjoyed it, and I'll see you in the next one for more about graph theory.